welcome to organic chemistry. I suppose we should start by defining exactly what we mean by organic chemistry. And the most common definition you'll see for organic chemistry is the chemistry of carbon and its compounds with just a few of the elements on the periodic table, mostly other nonmetals. So we're talking about hydrogen, nitrogen, oxygen, and the halogens primarily. But also sulfur and phosphorus. Quite a few cases. Okay. So these are all the nonmetals. And since they're nonmetals, they form covalent bonds. With other nonmetals. So in all cases here, we're talking about molecular compounds, not ionic compounds. And you probably remember the definition of covalent bonds is shared electrons, as opposed to a transfer of electrons from one species to another, which normally happens when you have compounds with metals with nonmetals, where the metal will actually give up its electron to form a cation, and the nonmetal will pick those electrons up to move to the next noble gas along the right-hand side of the periodic table and form an anion. But we're talking about carbon, which is a nonmetal, with hydrogen, nitrogen, and oxygen, sulfur and phosphorus, and the halogens, all of which are also nonmetals, and many of which are diatomic. Right? Hydrogen exists as H2, nitrogen is N2, oxygen is O2, all of the halogens as diatomics. Sulfur and phosphorus, of course, exist as covalent compounds. One of the most common allotropes of phosphorus is P4, which is simply a tetrahedral arrangement of 4 phosphorus atoms like that, with both pairs pointing out. That would be white phosphorus, which is the one that's pyrophoric and exposes or ignites spontaneously in air. And sulfur, which you may remember, exists as a crown-like compound, S8. So none of these elements exist uncombined in nature, except carbon, which can exist. It often exists as graphite, or as diamond, or as Buckminster fullerene, or carbon nanotubes, so often combined in nature. So organic chemistry focuses on carbon. Carbon is the most important element, and it uses a very small subset of other, mostly main group elements. We really won't be concerned much with the transition metals in this course, and we certainly won't be compared with the inner transition metals, or the rare earth lanthanides, or the actinides and transuranium elements. So we're mostly going to be concerned with just a little bit of the periodic table. And because of that, it's well worth learning the first 3 rows of the periodic table and the halogens and some of the other elements that we're going to see frequently, because you'll notice there's no periodic table in this room. Generally, I won't give you a periodic table on exams. So it's useful to just kind of know the portion of the periodic table that you're going to be working with. The other important thing to know is the definition for electronegativity. Because its differences in electronegativity, which usually has the symbol chi, and differences in electronegativity cause some bonds to be polar covalent bonds as opposed to non-polar covalent bonds. It's that polarity of the bonds that causes organic molecules to have their distinctive reactivity. So we need to remember the definition of electronegativity, which I expect you to remember from general chemistry, And that is defined as the tendency of an atom within a covalent bond. That's crucial. Only within a covalent bond does it have any meaning. To draw electron density towards itself. And I use E minus as an abbreviation for electron. So this leads to an unequal sharing of electrons, where one atom has a greater tendency to draw electron density toward itself than the other, which means that if it's sharing a pair of electrons, the one atom might have 1.2 or 1.4 electronic charges on it, and the other one would be left with only 0.8 or 0.6 electronic charges. So the electronegativity is the tendency of an atom within a covalent bond to draw electron density toward itself, and that leads to polar covalent bonds. And the amount of difference in the electronegativity is going to determine when something is a nonpolar covalent bond, which we generally associate with the differences in electronegativity of less than 0.4 units versus a polar covalent bond which has differences in electronegativity somewhere between 0.4 to about 2. So 0.4 is less than or equal to the difference, and that's less than or equal to 2. Sorry, I'll switch this around. 0.4 less than or equal to delta chi. Less than or equal to 0.2. Some textbooks will say 1.7, but 2 is a good number to use there. And then, of course, anything that's greater than 2 is an ionic bond. And since metals generally have very low electronegativities, in most cases, a metal combining with a nonmetal is going to have a difference in electronegativity of greater than 2 units, and therefore form an ionic bond rather than a covalent bond, and electron transfer instead of electron sharing. So nonpolar covalent bonds, diatomics, H2N2O2, carbon with hydrogen, because carbon and hydrogen differ by less than 0.4 electronegativity units, and polar covalent bonds would be carbon or hydrogen with many of the other elements mentioned, nitrogen, oxygen, the halogens, to some extent sulfur and phosphorus. So we need to know both the elements and names for the first 3 rows of the periodic table and the halogens, and we also need to know their electronegativity values so that we can determine when they're bonded whether they're going to be a nonpolar or a polar covalent bond and how polar. So you probably know hydrogen, and underneath hydrogen is lithium, and next to that is beryllium, and then if you continue, sodium and magnesium, and if you want, you can continue going even further down the periodic table beyond the 3rd row. Below sodium is potassium, below magnesium is calcium. And then we have the transition metals, which we're going to ignore because we just don't care. We have 6 elements: boron, carbon, nitrogen, oxygen, fluorine, and neon, and above neon is helium. We won't actually care about helium. It's used as a cryogen, so it's very important in chemistry, but it's not important in organic chemistry since it doesn't form covalent bonds. Below carbon, we have silicon. Below nitrogen, we have phosphorus. You may remember that these are known as the antigens. Oxygen, we have sulfur. You may remember that those are the halogens. And below fluorine, we have chlorine. You will remember that those are the halogens. And then, of course, these are the noble gases: helium, neon. Hopefully, you will also remember that with the exception of hydrogen, all of the other group 1 elements are in alkali metals. The alkali metals are extremely important in organic chemistry. What we're using is a counter ion where we have ionic compounds of oxygen or nitrogen or some of the other elements. And then if you want to, you can go even further down. It's not necessary to learn these, but you could know that underneath carbon and sulfur is germanium, and underneath nitrogen and phosphorus is arsenic, and underneath oxygen and sulfur is selenium. It will be important to know the other two common halogens, bromine and iodine. So fluorine, chlorine, bromine, iodine going down the periodic table. So this part of the periodic table, I will expect you to be able to reproduce on demand hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, and then potassium and calcium, bromine, iodine. You may remember that metals are on the left-hand side, non-metals are on the right-hand side. We have what we call semi-metals. Silicon, germanium are semi-metals. Arsenic is a semi-metal. Boron is a semi-metal. So kind of this diagonal, and then a couple on this diagonal. Right? Aluminum is a metal. Right? But gallium is a semi-metal. And germanium is a semi-metal. And then if you go down even lower, those are semi-metals as well. Non-metals over here. Semi-metal, really the only semi-metal that we're going to be very much concerned with is silicon, boron to an extent, and then the metals on the left, mostly as counter ions because they don't, in general, form covalent bonds. Well, there are some exceptions. Aluminum, for example, does form covalent bonds with bromine and iodine, although it forms largely ionic compounds with chlorine. So then we also need to know the electronegativity values. It's possible that you memorized the electronegativity values last year in general chemistry, but if you didn't, it doesn't really matter because you can find the table of electronegativity values on page 12 in your textbook, table 1.2. The numbers are slightly different in our textbook than they are in the, I use those, but if you didn't, you might as well use the ones that are in our textbook. So hydrogen in our textbook is 2.2, it would have been 2.1 in your general chemistry textbook. Lithium is the same, lithium is 1.0 in both textbooks. Beryllium in your textbook in general chemistry would have been 1.5, in our textbook it was 1.6. Boron is 2, that's actually the same in both textbooks. Argon is 2.6 in our textbook, we did 2.5 in the Gen Chem book. Nitrogen is 3, that's the same. Oxygen is 3.4, in general chemistry that would have been 3.5, and fluorine is 4.0. And neon doesn't have an electronegativity value, and neither does helium or argon, or the other noble gases for that matter. And you can probably tell me why. Because the definition of electronegativity is the tendency of atoms within a covalent bond, then you can't have a tendency to draw electron density towards yourself within a covalent bond. So the noble gases, since they by and large don't form covalent compounds, don't have measured electronegativity values. So you'll notice a trend. If you just remember one of these, it pretty much goes up by a half as you go to the right. 1 to 1.5, okay, 1.6 to 2 to 2.5, 6 to 3 to 3.5 to 4. And in the general chemistry textbook, it's exact. 1, 1.5, 2, 2.5, 3, 3.5, 4. Those numbers would be good enough. Oxygen's a little less than 3.5, carbon and beryllium a little bit more, and then 1.5 and 2.5 respectively. But in large degree, those numbers are kind of the same as the general chemistry textbook. As you go down the periodic table, the electronegativity drops. You know that the electronegativity drops as you go from right to left, and it drops as you go from top to bottom, and fluorine is set at 4, the highest electronegativity value. It drops a lot more on the right-hand side of the periodic table than it does on the left. So on the right-hand side of the periodic table, it drops by 0.8, from 4 to 3.2, or 3.4, sorry, 2.2. And then a little less, from 2.6, it goes down to 1.9, so it only drops by 0.7 rather than by 0.8 that it drops on these three cases. And then it drops by less, right, over on the left-hand side. So 2.0 goes to 1.6, it's only dropped by 0.4 there. 1.6 goes to 1.3, so we dropped by 0.3, and on the allied metals are very similar in electronegativity, all right about equal. Fluorine and chlorine are significantly different. The second row elements behave significantly differently from the first row elements, and one of the reasons for that is because of the larger electronegativity values as you go down. So they're going to drop by more as you go down the periodic table than as you go to the left in most cases. 4.0 to 3.4 going left to 3.2 going down, 3.4 to 3.0 going left to 2.6 going down, 3.0 goes to 2.6 going left to 2.2 going down, right? You can see that trend. Bromine is 3 and iodine is 2.7 in our textbook. So you'll notice that once you get down further, right, from the second to third row, there's a big difference of 0.8, but then from third to fourth, only 0.2, from fourth to fifth, right, only 0.3. The third and fourth row elements, or the second and third row, kind of in the main group, are much more similar to each other than they are to the second row. And that has to do with molecular size. It has to do with the fact that once you get into that third row, where the principal quantum number n is equal to 3, there are d orbitals present that are not present in the second row elements, where n is equal to 2, L can only be 0, s orbitals, or 1, p orbitals. You can't actually have L of 2 until you get n equal to 3. So there are no d orbitals on boron, carbon, nitrogen, oxygen, and fluorine, but there are d orbitals on the others. Right? So those are the numbers from the table, and you should endeavor to remember them. Basically, it's rising by a half each time you go to the right, starting at 1 lithium, and then it's dropping by 0.1, it's dropping by 0.3, it's dropping by 0.4, 0.7, and 0.8, 0.8, 0.8. And then here, 3.2 to 3.0, dropping by 0.2, and then dropping by 0.3, going from 0.0 to 2.7. These numbers, like I said, are slightly different from the general chemistry textbook. Right? This would be 1.5 in the general chemistry textbook, and this would be 1.2. This would be 2, and then this is 1.5 in the general chemistry textbook. This would have been 2.5, right, in the general chemistry textbook. And phosphorus and sulfur are a little different. That's 2.8 in the general chemistry textbook. I think that's 2.4. And then fluorine is 3.0 in the general chemistry textbook. And bromine is a little different as well. So that part of the periodic table is the part you're going to need to know. And I will give you the opportunity to show me that you do on the first quiz of the class, which will happen in the next period, right, where you'll be given a blank periodic table, and you'll be asked to fill out the element symbols, and you'll be asked to fill in the electronegativity values, and then you'll also be asked to define electronegativity, tendency of an atom within a covalent bond. So we're talking about non-metal bonds here, to draw electron density towards itself, nonpolar if it's less than 0.4 unit difference, polar covalent if it's between 0.4 and 2, and then ionic bonds if it's greater than 2. Yeah, there may be some exceptions there, but not too many. It's also important that you remember the difference between polarity. We talked about polarity in terms of a polar covalent bond and polarizability. They both start with P and end with ity, but they are quite different. Polarity is associated with an unequal sharing of electrons as a result of a difference in electronegativity we often show polarity in a molecule by, for example, in hydrogen fluoride, which we know is a very polar covalent bond, a difference in electronegativity of 1.8 between 2.2 and 4. We often show that with a delta plus and a delta minus, showing that the fluorine is pulling electron density towards itself. The other way to show that is to show a bond dipole where the positive end of the arrow is associated with the partial positive charge, and the arrow is pointing towards the partial dipole moment, mu, and you'll probably remember that's equal to the product of charge, Q, and distance of separation between the charges, d. Probably not that 1 divi is equal to 3.34 times 10 to the minus 19, or sorry, 10 to the minus 30 coulomb meters. So 3.34 times 10 to the minus 34, or times 10 to the minus 30 coulomb meters. Normally we're going to do charge in electronic charges. So lithium plus would be +1, and fluorine minus would be -1. And we're normally going to do distance on the atomic scale in angstroms, but if you convert the electronic charge to coulomb and you convert the distance from angstrom to meters, you get coulomb meters equals 1 divi. So that's polarity. But that's not to be confused with polarizability, which will become particularly relevant when we talk about acidity. Kind of one of the things you use when you don't know what you're talking about and you want to start thinking about organic chemistry. You just start tossing out words: electronegativity, polarity, polarizability, sterics, hypercon, over and over again. It's nice about organic chemistry because we don't introduce a whole bunch of new concepts. So polarizability is the ability of an electron cloud to distort in response to the approach a point negative charge. There is, of course, no such thing as a single point negative charge. But if you would imagine a negative charge on a point of a pin, right, that's a pretty good representation of a point negative charge. And a highly polarizable molecule will have this ability to distort in response to the approach of that negative charge. So if we compare krypton, for example, which is a noble gas that's got a very large orbital, and we compare that to neon, which is a noble gas with a much smaller orbital, neon will be holding its electrons pretty tightly. So if you bring a negative charge up towards neon, the electrons would like to run away. That's a repulsive force between that negative charge and these electrons. But the neon nucleus is holding those electrons tightly enough, they really don't have the opportunity to do that. Whereas if you bring a point negative charge up towards krypton, and krypton that tightly, what can happen is those electrons can distort. So you'll actually have the electrons kind of running away from that point negative charge. The electrons there. And being more on the left-hand side and less on the right-hand side. So after the negative charge approaches, instead of looking like this, krypton is going to look like this, where the nucleus is over here, and the electrons are all over here. And that's going to induce a dipole. Right? So we're going to have a dipole where the krypton nucleus is the positive end, and the electron cloud is over here away from it, and that's called an induced dipole, or an instantaneous dipole. I'm not sure which term you would use in general chemistry, whether you would have used induced dipole or instantaneous dipole, but that's the origin of the London dispersion force, which is the weakest of the intermolecular forces, and is also sometimes known as an induced dipole force. Instantaneous dipole and induced dipole are used interchangeably to represent the temporary dipole that caused by this negative, then this can in turn induce a dipole on an adjacent atom of krypton to form an induced dipole over there and result in the induced dipole force. So polarity has to do with differences in electronegativity in covalent bonds, and polarizability has to do with the electron cloud being able to shift and respond to the approach of an external charge. Right? So electronegativity, polarity, and polarizability, those are important definitions to know. And we have our variant table.